Dear all, I'm Dr. Bo Tang, an assistant professor in Southern University of Science and Technology. Now, let me introduce the fourth part of our tutorial, exploitations of low-quality SID. In this part, I will introduce three categories of low-quality SID exploitations. They are querying low-quality SID, analyzing low-quality SID, and the decision-making tasks among low-quality SID. In each category, I will introduce the problem setting and elaborate the representative studies. The challenges to conduct efficient and effective SID query processing are threefold. The first one is the uncertainty of SID, for example, location inaccuracy or discrete sampling. The second one is the dynamics of SID. It brings out data warning, data evaluation, data skew issues. The third one is the decentralized SID. It has data encryption and data heterogeneity problems. We summarize the key points and the corresponding solutions in the figure, and we will introduce the details of them one by one. Location uncertainty is the major issue in spatial queries. The probabilistic models have been widely studied to enable priority-oriented processing and data prunings. We categorize query processing techniques based on the type of location uncertainty they are handling in the context of IoT-based localization. In particular, it consists of two types. The first one is the uncertainty caused by inaccuracy of location algorithm. The second one is the uncertainty caused by the discrete sampling of devices. For the first one, uncertainty caused by location inaccuracy. The location of an object at time point t is usually described as a probability density function, which can be either continuous or discrete. Many queries have been processed in both continuous case or discrete case. For example, the KNN query, range query, rank query, reverse nearest neighbor query, and so on. To handle the uncertainty caused by the discrete sampling, a moving object O's location at unsampled time points are modeled by a distribution that is referenced to O's sampled and known locations. The distribution can be modeled to infer the location of a single time point or the locations across a time interval. Many techniques have been proposed in the literature. For example, uniform Gaussian self-defined function circulars for locations at a single time point. First order Markov Wing-Gris combination of road segments to infer locations across a time interval. In addition, the uncertainty models can also be applied during pre-processing to perform spatial interpolation of original data. Many approaches have been proposed to conduct efficient query processing over discrete sampling SID. We briefly summarized them in this table and refer the interested readers to our survey paper for more details. Queries over uncertainty spatial data have been studied extensively in last decades, while how to query uncertain data in a resource-limited and streaming setting remains open. The dynamics of SID bring out issues of data warning, data evolution, and data skew in spatial query processing. To efficiently process queries over massive SID, Distributed computing and streaming computing techniques have been proposed. For example, Spatial Spark was proposed to support indexed spatial joins and similarity trajectory search. Apache's DOM also used for spatial textual queries. For the queries over evolving SID, object locations and other information arrive continuously in a streaming fashion. Safe ranging and the incremental evolution strategies have been applied to reduce the communication and computation overheads. Skilled SID generated by the mobile users is seen commonly in IoT and cloud computing environments. For queries over skilled SID, node-node balancing and data partitioning have been proposed. For example, Ray proposed a heterogeneous cluster-based spatial query processing infrastructure that uses declustering to create balanced spatial partitions and dynamic load balance to resolve performance heterogeneity and data skew during processing. The research opportunities of efficient query processing over dynamic SID are twofold. The first one is devising high-speed yet low-cost computation algorithms. And the second one is conducting efficient query processing over decentralized edge computing nodes. For the second point, one of our work is accepted by VLDB 2022, which monitors spatial temporal quantile in edge computing environments. The result is error-bounded. We refer the interested reader to our VLDB paper for the technical details. In a distributed architecture, data encryption and heterogeneity pose challenges to query processing. Several techniques have been proposed to balance between data query efficiency and data privacy to elevate data encryption challenges. A unified data management and analytical platform have been proposed to address the data heterogeneity challenge. For example, it provides a unified storage and computation engine. The second category of exploitation of low-quality SID is analyzing our low-quality SID. There are many data mining tasks or data analysis tasks on low-quality SID in literature. We classified the existing analysis techniques by the quality issue related to uncertainty and dynamics. In particular, the uncertainty means the data inaccuracy and incompleteness. The data dynamics means data warning and data evaluation. Next, we will elaborate the techniques of different analysis applications. For example, trajectory clustering, anomaly detection, frequent pattern mining, popular path discovery. To address uncertainty in SID, many techniques have been proposed. They can be classified into three categories. The first one is probabilistic modeling. The second one is spatial temporal dependency. And the third one is spatial constraints. For trajectory clustering tasks, the data's location is inaccurate. A fuzzy vector representation was proposed to compress uncertainty and generate centroid trajectories to capture similar movements. Upon that, they conduct fuzzy C-means clustering algorithm over the generated centroid trajectories. For the anomaly events, the location trace is incomplete. A statistical model with the transition probability was proposed. For frequent sequential patterns, the location is also inaccurate. The sequential exploration are discovered by spatial temporal dependency. For the periodic behaviors, the sequence is incomplete. They discover reference spots via spatial temporal dependency to retrieve sequential stop-by pattern from unsettled RFID data. A probabilistic model was proposed to capture deployment and spatial constraints, find uncertain candidates based on the filtering and the mapping constructions. However, all the above-mentioned proposals are batch-oriented and centralized, and they do not consider real-time and decentralized setting. To handle high data volumes in analytics, indexing and pruning techniques have been proposed. For example, indexing and pruning have been used for trajectory clustering, nominal trajectory discovery, and core evolving pattern mining. Distributed computing for RFID trajectory clustering and sequential pattern mining. Online learning of spatial temporal dependency have been utilized to facilitate the analysis of evolving SID. How to migrate the functionality covered above to edge devices to reduce cost and latency are highly relevant future research topics. Last, I will introduce the decision-making tasks based on the low-quality SID. It is the third part of low-quality SID exploitations in this tutorial. The decision-making tasks including the prediction of next location, traffic volume, or spatial temporal variables, the recommendation of POIs, points of interest, or routes, and the planning of task assignments or site selection. We organize studies according to the data quality issue they address in learning. It has 5 parts. First, the scarcity of labels. Second, the limited availability of and bias of data. Third, uncertainty of the data. Fourth, dynamics of data. And the last is heterogeneity and decentralization of data. The scarcity of labels issue have been addressed via various learning techniques. For example, unsupervised learning, semi-supervised learning, and multiple task learning. Specifically, variational autoencoding are used to generate qualified trajectories for self-driving simulation and traffic analysis. To select new public toilet locations with limited positive labels of regions, Chen identifies reachable regions, construct a high order and semantic representation from multi-source urban data, and adopt a positive enabled learning over the representations to identify enabled positive regions that should have a toilet. A multi-task ordinal regression framework is devised that enforces similar feature sparsity patterns for different tasks while preserving the heterogeneity in their scale patterns. The limited availability and bias of data issue has been addressed in transfer learning and meta learning and federated learning. For example, to transfer long period data from other cities for spatial temporal prediction, Yao trained a well-organized spatial temporal network via meta learning methods. A federated learning framework for location prediction is proposed, which utilizes self-attention and local global fusion to achieve personalizations. Probability modeling is used to handle location uncertainty, while reinforcement learning is used to deal with incompleteness, in particular, to recommend next individual POIs. To recommend next individual POIs, with uncertain check-in and at a collective POS. Zhang exploits hierarchical category transition to model users' preference transitions and semantic relatedness of POS at different granularities. Using incomplete trajectories for traffic warning inference, a deeper reinforcement learning method was proposed to recover vehicle movement and use graph embedding to encode multi-hopper traffic propagation between road segments. Reinforcement learning and incremental learning and edge computing techniques have been exploited to address the dynamics of data. Consider imaging crowdsourcing worker in spatial tasks. Some propose gated recurrent unit-based predictors for tasks and workers, and propose adaptive batch strategies based on the deep queue network to predict the destinations in data streams. Naha and Pudunda apply a sliding window with the exponentially feeding to 4 incremental learning methods. Multitask and multi-view learning techniques have been adapted to integrate multi-data source data, while federated learning is used to facilitate decentralized models. For example, spatial temporal multiple task learning algorithm is devised to integrate multiple heterogeneous data sources for within-feed crop yield prediction. Zhang utilized the context-aware tensor decomposition and iterative multi-view learning to combine cell phone detail records and transportation data for improving single-view mobility inference. Liu proposed a federated learning based on GRU network for traffic flow prediction that updates universal learning models through a secure parameter aggregation mechanism, rather than by directly sharing raw data across organizations. For other related workers for other research workers about the data exploitation of low quality SID, we refer the interested reader to our survey paper, which published in ACM Computing Survey. Thank you.
Hi everyone, I'm Mohammad Amir Chima. I'm an associate professor at the Faculty of Information Technology in Monash University, Australia. I will present the last part of this tutorial discussing the emerging trends and future research directions in this area. So here is the outline. First, I will discuss the emerging trends, and then I will talk about the open issues and the future research directions. Okay, so let's get started. In general, there are quite a few privacy issues with IoT data. So it is important to design data management and analytics techniques for the spatial IoT data that are privacy preserving and secure. For example, the spatial IoT data is often encrypted, anonymized, or hidden due to privacy reasons. But ideally, this should not affect the usability of such data in relevant applications. So there has been quite a few recent works that focus on query processing, analysis, and decision-making on top of such encrypted or obscured spatial IoT data. Also, if you consider from the data quality point of view, it is important to design privacy-preserving data representations, such as embeddings, and also to develop effective cryptographic solutions. Spatial IoT data has become very important, and there have been many new privacy regulations. Thus, this area is likely to receive much more research attention in the coming years. Another area receiving significant attention is edge or fog computing, where computation and data storage is closer to the data sources. such as the IoT devices. A recent report from a market research firm, International Data Corporation, or IDC, predicts that more than 40% of IoT data will be stored and processed at the edge or close to the edge. So here, a key challenge is to address data quality issues at the edge devices instead of at cloud. This is challenging because edge devices typically have limited resources, such as limited computation power or battery, etc. Recently, there has been significant research in this area, and edge computing has been combined with several different techniques such as stream processing, blockchain technology, transport software-defined networks, lightweight AI specifically designed for edge devices, and system on a chip, etc. So the next one is reinforcement and incremental learning. This is another emerging trend for the data quality in spatial IoT data. This is because by nature, the spatial IoT data is dynamic and is updated continuously, and therefore there is a need for models that have capabilities to handle dynamic and incremental processing. Take this example. Many processes can be abstracted into reinforcement learning models such that the parameters are adjusted incrementally. And if you want to handle the data quality issues in spatial IoT data, several recent works have shown that reinforcement learning is effective in addressing data sparseness and data incompleteness. In many applications, IoT data is typically obtained from multiple heterogeneous sources. For example, urban IoT data is typically not only multi-source, but also multimodal and heterogeneous. So it is important to effectively integrate such diverse data. Therefore, this area is also gaining significant research attention. For example, many recent works have used multitask and multi-view learning to extract latent and high-quality features from such multi-source data. Also, some recent works have used transfer learning, federated learning, and pre-trained models to utilize diverse data to enhance the richness and expressiveness of the training data. Representation learning techniques have also been recently proposed that map heterogeneous and multimodal data to subspaces. This enables them to jointly utilize their information. Some recent techniques focus on data integration techniques to improve data quality and interpretability. All right, now we will discuss major open issues and future research directions in this area. Internet of Things may involve thousands, or in some applications, even millions of heterogeneous and dynamic devices. And this makes data quality management very complex. So it is important to design effective quality modeling techniques so that they can guide how each individual device handles its data and how it interacts with the other devices. Representation learning may be an effective approach here. For example, a graph can be constructed where the vertices are the decentralized IoT devices and the edges are the data dependencies between different IoT devices. So representation learning over such dynamic graph can be used to estimate and predict various data quality measures. Also, the goal function of a model can incorporate various factors such as resource constraints, spatio-temporal distribution of nodes, and external environmental influence variables. Okay, many existing works have shown that integrating spatial data from multiple sources is quite powerful and leads to improved or new application. Many important insights can only be obtained by mining broader data pools obtained from diverse data sources. But IoT data repositories in most enterprises are still in silos, thus their enterprises may be missing on valuable insights. So to construct the data pools from diverse sources is challenging and needs trustworthy protocols and data governance mechanism to enable secure and reliable data sharing across different IoT repos. These challenges need to be addressed. So here, blockchain and federated learning techniques may be relevant. For example, the blockchain may be used to authenticate data, and federated learning may be used to train models globally while safeguarding each enterprise's private data. Okay, another important direction for future research is the data quality aware task planning. In the Internet of Things data quality management, many different services are exploited, such as outlier removal, fault correction, compression, and interpolation, etc. It is important to conduct cost-benefit analysis for such data quality services so that one can understand how these can be applied to optimize the data quality locally and globally, depending on the applications and their goals. For an effective cost-benefit analysis, we need to take into account several factors, such as data quality modeling, evolving topology, and characteristics of IoT nodes, and the priorities and data dependencies of different data quality tasks. Cross-layer quality management is another important research direction. Currently, Internet of Things adopts a layered approach that separates data quality tasks with different goals and data scopes logically. However, the usage of general-purpose data quality services such as compression and interpolation, which are at the bottommost layer, has been limited. In order to support quality management, to support diverse applications, an important future direction is to modularize and containerize these services and to organize the resulting modules in a cross-layered fashion. This vision can be realized by using secure and efficient control protocols and interfaces which are compatible with edge computing and microservices. The last feature research direction that I will discuss is quality management middleware for spatial IoT data. Dynamic and heterogeneous nature of the spatial IoT data limit its effective utilization. To enable applications that better utilize spatial IoT data and to make quality management ubiquitous, a quality management middleware that fits in the IoT paradigm is needed. Such a middleware is expected to integrate the feature research directions that we discussed earlier. That's all from my side. Thank you very much. We are happy to take any questions.